So our next presentation title is Seismic Strengthening of Concrete Floor Diaphragms using FRP based on full-scale testing. And we have two speakers for this presentation. I would like to first introduce Enrique del Rey Castillo. Mr. Castillo is a lecturer at University of Auckland, specializing in the structural use of fiber-reinforced polymer systems. He is an active member of ACI committees 440F, 440S, 369, and 240, contributing to the advancement in FRP applications for seismic strengthening and structural resilience. His research focuses on enhancing the performance and durability of concrete infrastructure through innovative use of FRP composites. We also have a co-speaker, Mr. Aniket Borwankar. He is a senior development manager at Simpson Strong-Tie in Princeton, California. He actively contributes to the industry as a member of ACI Committee 440F, 440S, 369. Aniket has authored over 15 papers and articles on structural repair and strengthening. He holds a master's degree in civil engineering and has extensive consulting experience prior to joining Simpson Strong-Tie. So I welcome both of you.
Thank you for that. Thank you, Aparna, for the introduction. Today is only Aniket and myself here, but there is a huge team behind us. First and foremost, the PhD students, because they dedicate 24/7 of their time to this, and without them, this would not be possible. But even within the University of Auckland, I have another 3 colleagues in the civil and mechanical engineering departments. And then we have a huge team of engineers and suppliers and FRP contractors that are helping us to make sure that our research is applicable and we don't do something in the lab that cannot be translated to real practice. Especially, I would like to thank Griff and Mike from Simpson and Ravi from KL Structures. And they are putting a lot of their own time into this. Now, why are we doing this? This is the most important thing. Now, why are we waking up in the morning? The big problem that we have right now in New Zealand and also in parts of the US, like in California and the West Coast, is that the concrete diaphragms cannot transfer the tension forces between the different structural elements between the walls or the frames. Now, there are several reasons for that. The seismic hazard has increased, design has changed over the last 30, 50, 70 years, change of use, many different uses or reasons. But the main reason is we know more about seismic, we know more about earthquakes and about the structural engineering in this context. Because of this problem, I got funding from the New Zealand government, from the ministry, to investigate how we can use FRP to strengthen concrete diaphragms for earthquakes. Now, why FRP? Why not steel plates or steel bars? The main reason is practical. You can make, or a designer can make anything work on paper. It's just lines on paper or on AutoCAD. It's just numbers on a spreadsheet. But then when reality hits and we need to build this thing into the building, FRP is far superior because it makes everything much easier, bringing all the material into the construction site. It's safer to build, a lot of practical applications. All of that results in less labor and a cheaper option. So FRP is far superior, but we don't know how to design them. The very first thing we realized when we started this project is that all of the research, like virtually all of the research up until a few years ago that we started working on this, was on very, very thin FRP ties or FRP sheets, usually 1 millimeter, 0.04 inches. So that does not relate to real life. In a real building, we're going to have 3, 4, 5 times as much. And all of the research is in very short ties, often 200, 300 millimeters. and in real life we have several meters. So that is the first thing that we needed to do, characterize the behavior of FRP ties in a real scenario with real sizes, both with and without anchors. Then we needed to investigate something that is very critical for New Zealand, because this is partially funded by the New Zealand government, which is precast, hollow core precast floors. These are prevalent in New Zealand. We even have the Northridge earthquake to teach us that this is not a good idea. So we continued using precast floors until a few years ago. And then once we have those two, we are going to investigate, or we are investigating, the global behavior of the diaphragm, in-plane strengthening, shear strengthening, collectors, how it affects the whole building. This is both for New Zealand and US. So for the first objective on ties, we started with this relatively simple setup. All of these tests were carried out in Stockton, which is where Simpson Strong-Tie have their laboratory in California. And we did, I don't even know how many tests, to be honest, like 150 or something. It's very simple. It's a concrete block with the FRP bonded on it. We can have anchors in different locations. Then we grip the FRP and we pull up. We cannot see the FRP tie here because we painted it with black and white dots. So we can use DIC to track the strains. DIC is basically cameras that take pictures every second or 2 per second. And then the software can track the pixels and we can see the strains, deformations and strains as the test goes, which is what we have here. In this video, I'm going to start it in a second. In this video, we have the FRP tie here. We are pulling from the top. And in here, we have the load displacement. And this is synchronized. So basically, what we have is the load is picking up. It's completely linear. And then at some point about there, the FRP starts to debond at the top. Then the strain travels down. There is no anchoring here. So the load is going to be maintained at around 40,000 newtons and the displacement increases. So we have, depending on the length and the FRP thickness and the concrete thickness, we have certain post-elastic deformation in there. It's not a completely brittle system. Same as concrete. If we have unreinforced concrete, it's brittle. With steel detailing, we make it more ductile. It's no different than that. We, like I said, did a whole bunch of tests. We collected all the tests that we could find in the published literature. Through this, this is published, by the way, so you can find it on Google Scholar. Through this exercise, what we realized is that the debonding strain or debonding force is not only related to the concrete strength or to the stiffness of the FRP, but is the ratio of the two. So you could have, on one side of the spectrum, you could have a very stiff FRP and a very weak concrete. On the other side of the spectrum, you could have a very strong concrete and a very soft FRP. And that is the key metric here, stiffness of the FRP divided by the stiffness of the concrete. Now, through some simplifications, we came up with that equation, which is what we proposed in that paper earlier in the year, to calculate the debond strain. Now, this is the strain at which that initial debonding starts. It's not the final strain. Now, the problem is this test setup is an improvement over previous research in the sense that it's more realistic. Instead of having an FRP this long, we're having a 1 meter long FRP. We have thick FRP. It's better, but there are still a lot of uncertainty that we are not building into this testing program, especially in a seismic environment. We don't know the earthquake. We cannot predict what the seismic demand is going to be. There can be imperfections during the construction, during the life of the building. There can be changes in the building. If it's a car park, for example, they're going to have cars running over. We're going to have global deformation of the building moving everywhere. We're going to have out-of-plane deformations. We're going to have compression and tension cycles. There are a lot of unknowns in here that we cannot build into the research program. Because of that, we need to build further redundancy into the bond system. In other words, we cannot rely on the resin, on the bond, as a reliable load path long term. Luckily, I spent a lot of years of my PhD working on FRP anchors, and together with the work that many other people have done, we know how to design these FRP anchors. We understand them pretty well. We know how they fail, why, in which situations. So we can design these anchors in different ways, and they have been included into the latest ACI document. So then we moved on to test ties with anchors at the end. So this is the exact same thing as before. Strain in this direction, in the loading direction. Now we have an anchor in there. So we are going to see the initial load is elastic, then we have that debonding, the debond, the strain progresses down. At some point, the anchor is engaged, and then we have, again, purely linear elastic response, because basically what we have is a spring, it's elastic spring between that point and the loading point. That's all it is. And then something fails, either the anchor or the tie fails, right? But basically what we have now is a trilinear behavior where we can see the initial state is here at the beginning, then the debonding starts, and that length is going to change depending on the length of the tie mainly, and then we have the anchor being engaged. So we did a whole bunch of tests. I'm just showing some here. All of this is either published already or going to be published soon. We can calculate loads, that one from the equation that I had in the screen before, that one from anchor design. Now we are working to obtain those displacements. So we know at which point in the displacement range the FRP debonds, how long that plateau is, and how much extra deformation the anchor is giving us. And we are working through all of this. So this is with one anchor. Now, the problem that we often have in real life in design is that we don't have a space in the structure for one anchor. One anchor is not enough to transfer the load that we need. So we need to have more than one anchor. So the next thought that we had is, okay, so how far can we put these anchors so they work together? And we ran a whole range of tests. I think we did another 50 or 40 something, basically 12 inches apart. Sorry that I move from inches to millimeters all the time, but because I work with American engineers, I need to use American units, and because I am in New Zealand, I need to use millimeter units, so it's a little bit of a pain. Anyways, we have 12 inches apart or 300 millimeters, and we see that both anchors are working together. We put them 24 inches apart, 600 millimeters, like in the figure. They're still working together. So we decided to put them as far as we could within the constraints of the equipment that we have. So we put them 48 inches apart, as far as we could. And we can see that one anchor is giving us about 50 something kilonewtons. Double anchor at 12 and 24 inches have one slope all the way to 125 inches. When we put the anchors at 36 inches apart, we have a first anchor that breaks, and then the second anchor takes over. So we can control this mechanism up to a certain point by very carefully designing the anchors and the spacing between them. The next challenge that we faced is that these anchors are relatively deep. This is like 4 inches, 4.5 inches. So it's like 100, 125, 150 millimeters. Sometimes we don't have that thickness in real life. Sometimes we only have like 2 or 3 inches, like 50 or 75 millimeters. So we ran a whole experimental program testing anchors from 3/8 of an inch all the way to 5/8 of an inch inserted into the slab 50 and 135 degrees, 2 and 3 inches deep. And then this is going to be published in November. And then we observe the peak load and the failure mode, where we break the anchor. This is anchor rupture, or we have pull out and concrete cone failures. So now we know how to design shallow anchors that are installed into the slab at 90 degrees or 135 degrees. So I'm not going to be so arrogant to say that we know everything about FRP ties and anchors, but certainly we know a lot more than we did a couple of years ago. And I think we are relatively comfortable that this is enough for the vast majority of the design cases that we see in our desks. So the next step was to look at precast floors. Now, the problem here is quite complex. The summary, without taking too much time, is that in an earthquake, that column, this is not in scale, obviously, and that column is going sideways. That beam is going along with the column up to certain points, right? That section is going to rotate a lot, that one not so much. And the FRP tie is crossing that interface to anchor into that beam. Now, the main problem is that this is very flexible frame, often ductility 4, ductility 6, drift is like 5%. But the floor is precast, pre-stressed. So it's, by definition, is rigid and stiff. It cannot crack, right? So we have a huge incompatibility deformation in there, where that crack is one single crack and is quite big. On top of that, we have problems of very thin topping of often 2 or 3 inches. The steel is brittle. It breaks at 2 or 3% elongation. So we have a lot of problems here combined into one solution, which is the FRP tie. So there were a lot of questions from our industry partners, very well-known, reputable engineers, and from the ministry, raising questions. What is happening with that rotation? How is that rotation affecting the FRP tie? Is it going to break it before compared to the pure tension tests? Is the debonding mechanism different? What happens when we have both the rotation and the tension from the tie? What is happening with the anchorage detail there? How are we going to anchor that force into the beam without breaking the beam? What is the global response? A lot of questions, right? So we used relatively complex test setup, but once you get into it, it's actually not that complex. Basically, we have the beam, the support beam, the in situ beam that is rotating in that scenario, and then we have the precast floor with the 50-75 millimeter stopping, and the FRP is running on top. Is that red line? Then we have 2 actuators, one that moves up and down to simulate the rotation, and one that pulls the floor apart to simulate the tension. We have 10 of these tests. We have completed 6, all of them with rotation only. We haven't applied the tension yet. And the most important mechanism is in the negative moment, right? When we are going down and the FRP is in tension. So with all of that in mind, I'm going to talk about the first 3 tests first, because they behave very similarly. So we have a width of 200, different thickness of the FRP. The anchors are over-designed, and then we can see that the response is more or less similar. We have the FRP debonds at a lateral drift of 0.5, 0.75%. The strain that we measured in the test is not that different from the model that we published earlier in the year. Junri is the name of the student. And then the failure is very, very similar in all 3 of them, and is the failure that we want. We don't want to transfer the failure to the beam. We don't want the floor to fail because we only have the cables holding it together. So we have one crack at the interface between the slab and the beam, and it opens all the time until the maximum stroke of the machine, which is 6.5% drift. Now this is the backbone curve. The negative moment is here, so I'm gonna flip that so it's easier to understand. And what we can see here is basically the exact same thing that we were seeing in the pure tension tests. We have an initial very stiff elastic response. Then we have the debonding, which the load didn't decrease, the load was maintained. And then we have the anchor being engaged, which is basically a elastic spring. And this is the video. It's all the way at the bottom, 6.4% drift, not a strain. Basically, what we have is an elastic spring between the anchors at one end and the actuator at the other. 6.7% strain, the drift. So the strain is 0.7%, is much lower than the failure strain, and that's at 6.5% lateral drift. It's a very robust solution. Now the problems started when we increased the width of the FRP. Why? Because the loads are much higher. Now we have a 3 times more material without accounting for the width. Now the problem we had here is we had the anchors in 2 layers. We have 8 anchors now, and we have them in 2 layers or in two rows, and that creates a weakness. So we didn't debond the FRP. We just transferred the failure from the interface to the plane, the shear plane that the anchors are creating. We destroyed the beam and we broke the FRP at this point, at 3.5% drift. Still, the building is not going to collapse because it's 3.5% lateral drift. And these buildings have additional lateral systems like additional walls or steel frames to limit the drift to 1 or 1.5%. So the building is not going to collapse. But I don't like this solution. This makes me very anxious. The next step is we had still 8 anchors, 4 and 4, but they all finish on the same line. So they are all engaged at the same time. The problem in here is these 4 anchors were engaged before those 4 anchors, so the crack happened there. In here, all 4 anchors are engaged at the same time, so the crack happens all the way up there. The capacity is higher. We still crack the beam, but then the steel wraps in this direction were engaged at 1.5%. And then we debonded the FRP and eventually ruptured it at 6%. So this is a very good response, especially compared to that. I still don't like it because we are still cracking the beam. And ideally, we don't want to damage the lateral system. So the next step that we did, and we tested this maybe 3 weeks ago, we debonded that. The reasoning being that we want to release the stiffness. The bond is stiffer than the FRP by itself. So we want to release that stiffness, and we want to make sure that that interface opens. It worked very well. We got debonding at the initial lateral drift, similar to here, 0.5, 0.75. The very minor crack, all the way at 2% lateral drift, and the FRP rupture at the end. So this is a very successful test. The next test, we are going to try to play around with the debond area to understand it a bit better. But what this has taught us is that we can break the beam. So how do we prevent that? Luckily, ACI 318 has a lot of provisions for that, for post-install anchors, breakout capacity, group effect. All of these have been studied in a lot of depth for the last 20, 30 years. So we can calculate those capacities and design around them. So it's good that I don't need to look into that because I already have enough. But that means that we need to go back to ACI 318 and look at the capacity of the concrete itself, of the existing structure. Now, what is next? We are going to do 4 more tests, 1 more with only rotation, and then we are going to install the tension actuator to have both. This is going to be completed sometime early next year, probably around April next year. And what we are doing right now, from now to April, we are building these collector tests, which is basically a very big slab. I've never seen such a big slab tested before by anyone. This is about 6 meters. We are going to have the FRP on top. Sorry for the quality of the drawings, but the student is still working through them. And then we have the actuator pulling them apart. Aniket is going to explain later what we are hoping or expecting to see here, but basically is how we design FRP to restrain the floor from deforming too much. And with this, I'm going to move a little bit towards design, more useful, practical things. We are about to finish an update in ACI 440, chapter 12.4. Right now, chapter 12.4 is just shear, basically, and it doesn't work very well. It's no one's fault. It's basically the data that was available back in the day when this was written. But now we have better data, like I was explaining before, thicker ties, longer ties. So basically what we are proposing, and has been balloted already and is been, running its course, is that we have a component that is the contribution of the FRP, that is the area of the FRP times the stress, with the stress being, or the strength, being the modulus of elasticity times the design strain, and the design strain is coming from the equation that I showed before. So this is for American units, and this is for international units. Now, what is the actual implication of this on real design? I have this little slide here where I compare the old method in blue with the new method in yellow. Now, the interesting thing here is that the difference between the two is larger when we have thick ties and low strength. This is about 3,000 psi, I think, which is where it's more common to have these situations in real life. Basically, the strong concrete thin ties that is prevalent in the published research doesn't change too much, but in real life applications is where that change is more significant. It's like 50%, right? And with this, I will pass it on to Aniket.
So yeah, thank you, Enrique and Aparna, for introducing me in the start of the presentation. So taking all the work that Enrique had done and others had done so far, we mostly in the US are basically designing collector elements regularly. We have a building which is deficient, its diaphragm is deficient. Typically, engineers are coming back and building new lateral system. They're building new shear walls in the building. Most of the times, your slab doesn't have the tensile capacity to carry or drag the forces to your new lateral system. So we are using FRP as a tensile member to drag the forces from your slab back into your lateral system. And what is the best way to do that? So taking all the research together, what we put up a design philosophy for collectors based on the research, and then we are going to also test it out in the full-scale test that Enrique mentioned. So in all the tests that we saw so far, we know that FRP debonds when at the cracks when the strain gets very high. So these are existing buildings, these are existing slabs. Like Enrique mentioned, they have some imperfections in the slabs, and as your slab cracks, which most of the time in an earthquake your slab is going to crack, and the strain gets higher, your FRP is going to debond. I think we've seen that in a lot of tests. We know this behavior pretty well. The problem with seismic applications, again, as Enrique pointed out, is we just don't know where these slabs will crack and at what strain in the concrete and a performance level these slabs are going to crack. So a good assumption is that at the ultimate condition, which is your ultimate design load, you're going to have large seismic debonds and demands, and your FRP is going to crack eventually at that location. So that's, again, a fairly good assumption based on the test that we have seen. Collectors elements are likely to debond from the concrete in some locations while staying bonded in the other locations. I think this is also fairly well understood. Where you have cracks, your strain gets higher, your debonding occurs at those locations. And this again depends on local cracking, how much stiffness variations you have in the different connecting elements, and your actual strain demands. Again, from tests, we know that FRP anchors help to control the debonding and allow the FRP to continue carrying the load. So once your FRP completely delaminates, it's going to just keep on delaminating like Enrique showed in the video, and it's not going to have the load carrying capacity. You're going to lose your load carrying capacity. So if you have anchors every so often that is anchoring your collector back to the slab, you're still maintaining that load transfer between the FRP element and your concrete element. And the last thing is design of collectors should look to provide enough FRP and enough anchorage. So there are two components to it. You need to provide enough FRP and you need to provide enough anchorage. So far, I think in the industry, the engineers would look at a load demand. They would calculate how much FRP they would need to meet that tensile capacity. But the second part to it was how do you adequately detail it? Something that we do in steel every day, right? In steel, we calculate how much amount of steel we need. How do you detail your steel? How do you hook your bars? I think that step was missing in the industry. And I think with more testing, we are realizing that that's an important step to ensure that you get the performance that you're looking for. So working on this, we sketched up some very simple sketches of what we think happens in a collector behavior. So the blue is your existing diaphragm. You have your lateral system, which is most of the times a concrete shear wall. And then you have the FRP, which is the black line on the top. And then you have some anchors. And again, the question is what is the spacing, but you'll have some anchors at a regular interval for this collector element. So we know that the adequate stiffness of FRP works with the concrete slab. I think the key is that we shouldn't make it too stiff. If your FRP is too stiff, it's going to debond earlier. Most of the times we are designing this to a higher level earthquake, but I mean, if you're on the West Coast, you do get these smaller earthquakes regularly. The bond between FRP to concrete is most of the times enough for smaller earthquake levels. But if you're doing it in ESC 41, BSC 2E control levels, you are potentially going to have this debonded, and then your anchorage is going to keep that load transfer mechanism going. So why do we think it makes sense? Is again, it's the same sketch right here. At some point, you start developing your crack, which is this black line right here represented in the sketch. Where your concrete cracks, your FRP tends to delaminate in that area. Again, if you have enough anchors, that delamination is restricted between two anchor points. So as your crack starts to grow, your FRP delaminates. It's restricted between the anchor points. Again, it's an earthquake event. At some point, another location in your slab is going to crack. Again, at that crack is going to increase in width. Once that happens, your FRP is going to delaminate at that area. At the same time, your slab starts cracking somewhere else. Again, you start debonding somewhere else. And then at some point, this is in your ultimate state or in your limit state, you'll potentially have an FRP strip that is delaminated, but all the anchors are still going to help maintain that load path. If you think of a collector element, right, this is a load diagram. A collector element typically starts with 0 kips at one end of your diaphragm and gradually increases and delivers the maximum force into your lateral system. So this goes from 0 kips, and every feet of the slab, it's picking up a certain amount of load, and then it keeps picking up, and then at some point it goes and delivers it all to your lateral system. So if we are able to design these anchors to ensure that that load transfer, the shear lag or shear effect, you're still keeping on engaging the collector, you're still transferring the force into your FRP. Even if your FRP delaminates, you still are maintaining that load path in case of an earthquake. And this is again very similar to your steel plate. And going back to a steel plate, if you're putting a large steel plate on a slab, you're typically never just going to rely on the bond. You're going to have some amount of anchorage detailing involved. And so the similar concept is potentially works for FRP as well. So again, looking at the design philosophy, provide enough anchors to ensure that the load path can be maintained, even if the FRP totally demands that the bonds at the BSE 2E, which is your limit state. Calculate area of FRP. Similar to that, you would do it with steel. And then once you do all that, you have to ensure that you have that load transfer mechanism, right? You can either do it with steel angles, you can do it with FRP, but all that force now has to go from the diaphragm or from your FRP collector to your lateral system, which is a shear wall in this case. So taking all this together, a summary for collector design, and this is kind of important because there is no good guidance. We are looking at publishing this. Enrique kind of showed the first equation, but ACI 440 now has a ballot. It has a task group that has come up looking at all the data that Enrique showed of what is the debonding equation for an axial tension strengthening capacity for an FRP member, and a collector is a tension element. So the new proposed equation is what's given here, the 0.28 times this term right here. You can calculate your debonding strain. Again, as you add more FRP, the debonding strain goes down. It's also a function of your concrete strength. So get your debonding strain with this equation. Provide anchors to ensure that the load path can be maintained even if FRP debonds. I think we've seen that through testing as well. Maintain adequate force transfer between a collector element and your lateral system. And again, FRP is a tension member, right? You still need to check your concrete for the compression, because in a collector, you get tension compression cycles. And you want to ensure that your concrete has enough compression capacity for that collector force. So this is our design guidance for collectors at this point. Going forward for in diaphragm shear, so moving along from the collector behavior to more of a shear behavior of the whole diaphragm. And the goal of this was to investigate the effectiveness of multi-layered anchored and unanchored CFRP retrofits and improving the shear strength of diaphragms. And the goal here was to explore reverse cyclic tests. So there have not been many cyclic tests on full-scale concrete diaphragms or half-scale concrete diaphragms, but essentially larger specimens. We wanted to look at different effect of FRP layup and anchoring. We wanted to compare the stiffness, ductility, strains, crack patterns, if you anchor it, if you don't anchor it. And the key here was to do in realistic type of base materials. So in most projects, I think in the West Coast, in California, on older buildings, you have concrete between 2,500 to 3,000 PSI concrete. So we wanted to keep the same type of concrete. We wanted to use very less steel in this test program, again, trying to replicate what steel is there in existing buildings. And we wanted a lot of FRP, again, that we do that on projects every day. We wanted to make sure that putting more FRP, what is the behavior of your member, of your diaphragm element. So these tests were done at Virginia Tech. So I wanted to acknowledge Eric Jacks and his team in Virginia Tech for all the test setup, design of the test setup, and we worked with them on this test program. So the test setup that Virginia Tech University came up with was approximately a 10 by 10 slab, and this is a 4-inch thick, 102 millimeter thick concrete slab. You have a shear wall on one side, which kind of is similar to what you would have in the building. You have some edge beams, chord beams right here in these two directions. You have an edge beam here. And if you look at the picture on the right, they cast two diaphragms at the same time. They had walls on one side, and then they had an actuator that was pushing and pulling this diaphragm through the steel channels or loading channels that you can see in blue on the sketch. Once they finished the test, they would move the actuator onto the other specimen and test the other specimen. So it was kind of an efficient test setup design where they could do two specimens at the same time than just one specimen. So the three tests that were done after they did a series of 6 tests for an ACI project, we used about 2 layers of 0.04 inch thick CFRP material. So because this is diaphragm shear, your loading is in one direction, all the FRP was oriented north-south in this figure. We had anchorage, and on the ends of the diaphragm or the ends of the specimen, you see here 2 rows of anchors, because if you put a single anchor, the anchor becomes quite big and it's not feasible to install a big anchor in a very thin slab. And again, based on the chart that Enrique showed, up to a certain number of anchors, if you put these anchors in series, they are able to share the load between them. Now, it's reasonable to think that that behavior goes on till 2 or 3 layers of anchors, but once you exceed that, then that behavior is no longer valid. So for example, you cannot just put 5 or 6 anchors and say that all these anchors are going to contribute equally to your total capacity of the member. So we wanted to make sure that we don't break the anchors. So we provided enough anchorage on both sides. The next specimen was again the same amount of FRP, but we completely eliminated the anchors. And this was just wanted to see the behavior of the anchors versus no anchors. And then the last specimen was actually we took the FRP and we installed the FRP in both directions. So you had FRP layers in left to right, and you had FRP layers north-south, and then we anchored on all sides of the diaphragm. So FRP north-south with anchors, FRP north-south, no anchors, and FRP both directions with anchors in all directions. So this is a test video that shows those specimen with no anchors. So you'll see that the FRP sheets are basically going left to right. This is your shear wall location right here, and this is where you're loading the member. And I'll start the video soon, but this is giving you an isometric view. This is giving you a plan view of the specimen, and we can kind of see the behavior. So like most cyclic tests, nothing really, happens at the beginning of the test. So it starts with smaller load cycles. As your load cycles start to go up, you'll see that the specimen now is moving in left to right direction here. You'll see the same thing in both the videos here. And one thing to note here is just keep, maybe on the left picture is better to focus on the left picture there, because that gives you a good idea about what happens to an unanchored FRP. So if you don't have enough anchors, and this is obviously a time-lapse video, so you'll see that at an instance, your FRP completely delaminates. So because there is no anchors, your FRP delaminates, the strip delaminates in an instance. So I'll just quickly play this again. So in a fraction of a second, all your FRP is essentially delaminated, and you lose your entire reinforcement in a quick instance. Something that is not quite desired on an actual project. So this is the CD9 specimen. So this has FRP now in both directions with anchors on all sides. And just I'll quickly play this video while I talk. So it's again the same test. This test actually had much less steel than the previous specimen. So we actually had number 3 bars at 18 inches on center, so very less steel. The previous specimen had number 3 bars at 12 inch on center. So the contribution of FRP is actually a lot more in this than the previous specimen. But as this keeps cycling, and I'll kind of expedite this a little bit in the interest of time. Okay, I'm not going to do it, otherwise my computer may hang. But you'll see that the specimen is moving, and at some point it starts to delaminate, but the anchors is holding it together. And what you'll see that at those high forces, your specimen now at some point is just going to start sliding, which you'll see in the one on the right. So right here now you see that the specimen just is sliding at the edge right here. So you were able to get a much better response, and all the concrete there starts failing. Your shear transfer between the wall and the diaphragm is not enough, and your specimen fails. So you're able to change the failure mechanism at a much higher force level than the previous specimen. Some pictures of the specimens. So the one on the left, two pictures, top view and bottom view of the specimen, is the specimen with FRP in one direction with anchors. You developed your shear crack. And if you come on the bottom of the specimen, you developed some concrete damage, which is similar. At some point, you got some shear transfer type failure at your wall location. But most of your diaphragm was in pretty decent shape. The one with no anchors is the two pictures in the middle, where you pretty much didn't have much of a slab left. So you lost all your FRP on the top. On the bottom, you come down and see that all your slab was just started to fall down. And then the picture on the right is FRP in both directions. Again, the slab was in much better condition. You just had this shear transfer, sliding shear failure mechanism at the joint, which again we can repair it with FRP or steel angle, but at least we were able to change the failure mechanism. We didn't get a drastic failure when we didn't have anchors. So again, anchors do a lot on your project if you're adequately detailing your FRP. So looking at all those three tests together, ACI 318 currently has a limit of, and 440 talks about 8 square root F prime C as the limit for your diaphragms. All the three tests were much higher than that, with the specimen with FRP in both direction being the highest. So it went about 14 square root F prime C. But again, there's not enough research at this point to say that, oh, you should go well beyond 8 square root F prime C. I think there's more research needed to validate this, but at least we were safely getting over up to the limit that's there in ACI 318. So we didn't stop there. So there was a lot of projects that we see are also on lightweight concrete specimens, and ACI 440 currently doesn't address lightweight concrete specimens, and that is because there is no testing on lightweight concrete specimens. So when a slab or a member has lightweight concrete, how do we design FRP? And there are varying thoughts, right? Some thought is, okay, it behaves similar to normal weight concrete. So you use the same equations, you design it the same way. What we've typically done is take a reduction of a lambda factor, which ACI 318 has a reduction for lightweight concrete. So use the same concept, but we really wanted to do a test and see what lightweight concrete does. And these tests were done very recently. So we did see a significant increase in FRP. So the one on the right is a control specimen, the one on the left is a strengthened specimen, and I'll kind of show some videos. So the video here is a control specimen. Again, the setup is the same. Now you have a concrete slab with no FRP on it, so you'll see the failure quite well. Very deficient in internal reinforcement, so you see all your shear cracks being developed in the specimen, and then all the cracks started to intersect and you get a shear failure of the concrete specimen. Pretty well understood. Looking at the FRP strengthened specimen, again similar to what we saw, the FRP here was in both directions. very similar to what you saw there, is the specimen held pretty well. At some point, you just lost your shear transfer between the specimen to the wall and had a sliding shear failure mechanism at that point at a much higher load. So this was again at about 1314 square root F prime C. So if detailed very well, the FRP gives you really high capacities. So this was a cantilever diaphragm test. Just to highlight the importance of adequate anchors, we also did some tests in our Simpson lab on specimens which were not cantilevered. So in these specimens, these were again low strength concrete and high strength concrete specimens with very less shear steel in between. And these specimens were actually loaded here in between rather than doing it at the end. We loaded these specimens in between right here. We had strips of FRP. We anchored the FRP well enough. This is the test setup where we had a control specimen. We had actuators in both directions, putting a cyclic load in the specimen. So this was pushing on from the right. Then when this retracts, this actuator pushes it, and then you have this cyclic loading of the concrete specimen. The control specimen failed in shear, which was again designed to do that. It doesn't have enough shear steel. You get your 45-degree classic shear crack that you would expect from the specimen. This was your strengthened specimen with FRP. It actually got a much higher force. Unfortunately, it failed in compression because the force went that high. But at that point, FRP had done its job. And this is kind of a similar DIC video. In this case, just look at the slab as it's moving up and down in the middle here. You have strips of FRP going north-south. All these yellow lines are cracks that are developing in your concrete specimen. The FRP is bridging across the cracks. The FRP is all anchored, so it's holding the specimen together. And then at some point, as the forces get significantly higher, you're just crushing the concrete at this location. So we'll see that shortly. And that's where your crushing happens. So if you just quickly look at this picture right here, right before the crushing, you have massive cracks in concrete. The FRP is kind of holding all those cracks together. Anchors are holding quite well. So again, if designed correctly and detailed correctly, FRP can add significant strength to your diaphragms. So coming up with a shear design guideline. So Professor Jacks and his team at Virginia Tech actually provided this in a report to ACI. When you're calculating the shear capacity of your specimen, you're looking at your VC, which is the strength of concrete. The VS is your strength of steel, and psi FVF is your contribution from FRP. We are still recommending a reduction factor of 0.75 for one-sided retrofit. You're calculating your VC, VS, normally how you would do it. You're using the same ACI equations for calculating the shear capacity of your FRP. You're using the debonding strain that is there in ACI 440.2 with on 11.4.1 equation. This is the shear debonding equation in ACI 440. And if you're doing lightweight, our recommendation is to use a lambda factor, a reduction factor, depending on what your lightweight is, concrete is. But this kind of follows the same guidelines that is there in ACI 440 today, except the use of anchors. So the use of anchors is important to achieve the performance that you're looking for. Moving on to flexural behavior of diaphragms, which is essentially your cord members. And I'm not going to talk a lot about it, but there was a good amount of testing, about 40 to 50 specimens that we did. This results of about 22 here that were again done in Stockton. Enrique and his team analyzed the results for that. You had a specimen with very less flexural steel. We put cords in both directions, which are your FRP strips. We again load it in the middle here. Tests were done on unanchored strips. Again, tests were done on anchored strips at the end. and then the tests were done with anchors in the middle. So these anchors in the middle kind of followed the guidelines to break the ties. So these were pretty massive anchors in the middle. As you'll see, that's not how you should design your intermediate anchors. So just FRP with no anchors, like Enrique showed in his graphs, it's mostly behavior is linear elastic. It goes to a certain point, you debond your FRP and you lose your capacity. There's not much deformation capacity in your member. As you look through anchors at the ends, which is basically at 8 feet on center for your longer ties, you get higher capacity and you get good deformation capacity, right? You're still debonding, but your anchors are holding it together. Really good performance of what you would want or expect in your seismic applications. And then with intermediate anchors, you get kind of a mixed behavior. You start losing strength. Again, your deformation capacity is not that high. This is because these intermediate anchors are quite big and you actually ruptured your strips. So our guidance to use intermediate anchors is to use smaller anchors, which was what Professor Jacks also presented in his ACI summary, is those anchors should be smaller so that they are able to share the load and the stresses can transfer beyond those anchors up to the end anchors. So anchoring again is important, as we keep saying, for the duration of your presentation. So just how do you design these cords? So a summary of the tests that were done. So unanchored cords result in a reduction of your deformation capacity. End anchors increase the moment capacity without compromising your deformation capacity. Middle anchors, especially for larger diaphragms, right, where you're putting these 100-foot long cords, you just don't want to anchor it at the ends of the cords. So your middle anchors need to be designed so as you're not concentrating too much stresses at those at that anchor location. So they need to let stresses go beyond them. ACI 440 currently have flexural provisions in flexural debonding equation. For cords, it's probably a good equation. You might consider taking another reduction factor because the ACI 440 equations are based on beam flexure, where you're really held by the curvature, but in a collector, in a cord or a collector, right, you don't get the benefit of that curvature. So you may take a 0.85 or some reduction there. And then anchors should not be spaced more than 8 feet apart based on the geometry of the test specimen. So again, adequately anchoring helps the performance on your FRP strips quite well. Just wanted, like Enrique mentioned at the beginning of the presentation, a lot of people contributed to this. Virginia Tech team was very instrumental. Enrique already pointed out to University of Auckland, Ravi Kanetkar with KL Structures, Simpson Strong-Tie team, especially the lab team, where hundreds of these tests were done in the lab. And Garrett Hagan with Degenkolb, who actually helped a lot of data analysis and coming up with these guidelines for design as well. And that's all I had from my side.
Great. Thank you so much, both of you, for your excellent presentation. This was like a whole, a bunch of, or you have compiled it so well that starting from the experimentation till the numerical study. So it was really good. We have few questions. The first question is, do we expect any contribution of FRP in the compression in these tests? And in what way are FRP contributing?
Do you want to go ahead, Aniket, or do you want me to take that?
Yeah. So FRP is not necessarily going to contribute anything in the compression cycle. So it's a purely tension member. It's going to contribute to your tension capacity of your member. In the compression cycle, what we have seen is an FRP as your crack opens, and in the compression cycle as the crack closes, there is a tendency for the FRP to buckle out of plane, for lack of better words. So again, anchoring helps to keep the FRP down, but the FRP will not help much in the compression capacity.
Yeah, that buckling depends on the application. We saw that in the shear tests that we have in front of us right now, but I didn't see that in my precast tests. So it depends on the application.
Yeah.
So our next question is, so do you plan on doing any field implementation of these tests or of these slabs which have been casted in the laboratory?
We do that every day. I have a consultancy company in New Zealand, and I am the equivalent of the American, what do you call it, Aniket, professional engineer?
Yeah, licensed engineer.
Yeah,
So
licensed engineer. And Aniket works for Simpson Strong-Tie, so this is being implemented on a daily basis.
Great.
yeah, I mean, it's implemented these designs. Unfortunately, there's no consensus on the design, like how should collectors be designed. And I think this presentation is aimed at showing the data that will help bring some consensus to that.
Okay. Our next question is, so you showed the data which is not in ACI 318 and 440. So do you plan on presenting this data to the committees?
Yes, so we have been doing a presentation for ACI. So we both, myself and Enrique, are members of 440F committees as well as 369, which is now started to look at seismic strengthening. So we do regular presentations in those committees. In addition to that, Enrique's team has been publishing papers pretty regularly on this. We actually recently also published a paper in FIB on diaphragm design guidelines in the US. So that is been accepted. I think the FIB is in November this year. So the paper will officially be published then. With respect to shear test that I showed, we did publish a paper with Virginia Tech team at the CEOC convention a couple of weeks ago. So yeah, I mean, I would say, Enrique, in the past couple of years, we have at least 7 or 8 presentations or publications with all these different research that is out right now.
Yeah, and all of the data, I think it was something like 1,800 data points were used for developing the new 12.4. All of that data was shared and discussed with 440F, and now it will be discussed with 440 main.
Great. Moving forward with our next question, what would you consider the mechanism in which FRP is contributing in all these?
That's a very broad question. It's basically providing tension, and it needs to be understood as what it is. It's a very anisotropic material that can only take tension in one direction. So you need to be very careful where you apply it, and not. One problem that we see almost every day is people think that this is this magic material that you can just draw some lines on AutoCAD and now the building is magical, and it doesn't work like that. It has its limitations like any other material. So I think the most important thing is for engineers to educate themselves on what this material is. It's not just a steel with a different modulus of elasticity and a different strain. It's not that.
Yeah, I agree.
Yeah, and hopefully, what engineers currently do is they just provide a force on their drawings right here, and then somebody else comes back and designs the FRP. I think the hope is for engineers, because this is such an integral part of the retrofit of the design that they are putting forward, that they understand how FRP behaves and then starts incorporating this in their designs and not necessarily as a deferred submetal.
Great. Thank you so much, Aniket and Enrique, for the presentation and also for answering all the questions. With this was the last presentation of our virtual seminar series. Before we go, I have some announcements. So we have Similar to this one, we have a next virtual seminar which will be on October 16th, and the topic will be advancement in polymer utilization in 3D printing construction. So please register. It's the same process. You have to go on ACI website to register for this one. And also, as I have already announced it before, next has request for proposals for 2025 funding. There are 13 topics on like where you can send your proposal. If any of these topics aligns with your research interest, please send us the proposal. More information can be found out on www.nonmetallic.org /requests for proposals. If you click on each of these titles, you will get the RFP notice for individual topics. If you have any questions, please email to me or at info@nonmetallic.org. With this, we end this session. Thank you so much. Thank you for attending, and see you at the next session.